Okay. Hi everyone. Thank you for being here again. I'm aware that this is very late in the afternoon, so I'm going to try to make this as quick and painless as possible. I'm going to be talking today about distant gravitational radiation from bridging pulsars. This is work that I did as a summer student with my supervisor, Professor Andrew Milato's, about 3 years ago, and it just kept growing and growing and growing. So it's been about a 3 year long summer at this point. But finally, it just ended with the publication of this paper about 2 weeks ago. So here I am talking about this. This work was done in collaboration with Julian Carlin and Josh Howard, who were at points PhD students at the University of Melbourne as well. So thank you. So let's get started. The natural place to start talking about my work is to talk about pulsars. So if you're not familiar, pulsars are rapidly spinning neutron stars with radio jet coming out of their magnetic poles. Their magnetic poles are misaligned with their rotational poles, so the radio jets kind of sweep past the Earth like the beam of a lighthouse, allowing us to time them very accurately and to figure out their rotational frequency from this radio timing. And of course, when we do so, we see that the pulsar, the rotation of the pulsars are slowing down. It makes sense. Electrodynamics that are rotating magnetic dipole it's going to radiate away energy, which leads to the slowing down of the pulsar. But that is not as simple a story as it sounds, because sometimes when we time these pulsars, we see an occasional abrupt increase in observed frequency, like the plot here, where the pulsars are slowing down, and then suddenly they. We see this in about 10% of pulsars, so it's not entirely uncommon. So a natural question to ask is what causes these increases? So in order to explain them, I got to talk about. We're not really sure why a neutron star. I suspect Pawlowski knows. He's just not telling the rest of us. But what we know for sure is that neutron stars are very cool. Yes. So there's probably some sort of neutron superfluid inside the star. And the reason why this is important is because superfluids rotate by forming vortices. They're not like a cup of coffee with a star, but instead they would rotate by forming these sort of essentially units of angular momentum. They're not quite that, but for the purpose of this talk, you can think of them as sort of units of angular momentum. And they kind of threads the star, let's say. And there are about 10 to the 15 of these vortices in real neutron stars. And for the purpose of this talk, our neutron star will look like the diagram I'm showing on the top right, where you've got a crust on the outside, and then the neutron superfluid inside with the vortices threading the whole star. And in neutron stars, these vortices have dynamics that involve propulsion and inside the star, like ion lattice defects, and the balance of these two different aspects of them causes something called vortex avalanches, which is the leading theory of how we think pulsar glitches occur. So let me take you through how a vortex avalanche a pulsar glitch. So we start with this sort of top view of a neutron star, where you've got the crust rotating and the superfluid also rotating with these dots representing fluid. At the start, the whole star is kind of co-rotating together, but because there is electromagnetic braking by the magnetic dipole rotating, as I mentioned before, the crust kind of slows down. And when the crust slows down, it's got some differential rotation with superfluid, but because these vortices are pinned to inhomogeneities inside the star, it can't really slow down with it. The only way it's going to have to slow down is by sort of expelling the vortices, and it can't do that because the vortices are pinned. So some stress will build up, and these vortices and the stress builds up along with the differential rotation until one of the vortex accumulates to a pinning site. This is called unpinning. And once one of them unpins, they would knock onto another vortex, and then they knock onto another vortex, and causing a cascade of unpinning events we call a vortex avalanche. And when this occurs, a whole bunch of vortices unpin at once. They leave the superfluid, they transfer angular momentum to the crust, things are glitch. And when this happens, then the whole star relaxes and we start over. Um, so, so what? In this kind of picture, we notice that in between the alpha lines, the current is pinned. So because frame current is kind of constant, and more importantly, it is a constant. Uh, it is pinned asymmetrically, I should say. This means that the star has current in the frame that's rotating the star, and because the star is rotating, you've got a current moment that's rotating. And we also figured out that this is going to emit gravitational waves, right? And these kind of signals is going to be basically constant until the next step. So it's going to be basically a sine wave with the frequency of the rotation of the star until it glitches, and then it changes to a different sine wave phase and it frequency of the star. And then it glitches and it does it again. So the big question that we're trying to answer is how loud this and the only way to do that is to calculate the current quarter-pole moment. And then a paper by Hugh Thorne in 1980s will, take us the rest of the way and give us a train. However, there are challenges because these vortex avalanches, as I've shown, that I've described before, are dominated by long-range interactions. It's a sort of self-organized critical system. The statistics, dynamics out of equilibrium. So the basic statistical mechanics doesn't quite work, and we can't really have any analytic theory to describe it. If you're familiar with sand pile systems, there's no way to just write down the answer. So how do we deal with it? So George that captures a lot of the features that I talked about, pinning knock-on dissipation, all sorts of things. George code ran up to about 1,000 vortices or so, and produces this animation that I'm showing that you can see sort of glitches happening occasionally. And yeah. So what I've done is I took George's simulation, current quarter moment from the vortex configuration. The Q here on the y-axis is basically the current quarter moment, physical constants as a function of the number of vortices NB. Now, when we do this, we can see that there are, for a particular number of vortices, you can have multiple values of current quarter-pole, and the reason for that is because this is an entirely stochastic process. You can, you can have a bunch of different possible configurations that correspond to the same number of vortices, right? So we constructed a statistical model motivated by the statistics which is the plot that I'm showing to the lower. See the paper for more details. And then we fit this model to the data so that we can get the scaling between the current quarter-pole vortices. And then once we do that, we can convert it to the H naught, which is the amplitude of frequency of the rotation frequency. And then we extrapolate. So I gave this talk at last year. I didn't have any this is the result. But we're not quite done yet. And if you have not dosed off yet, you can notice that neutron stars have about 15 vortices per dimension, while simulation contains about 10 to the 4. We're extrapolating 12 orders of magnitude, which is very, very dangerous. So the solution is to look at analytic scaling in response to the extreme cases. We do so. So I mentioned before that avalanche is and repulsion. So we looked at the case line and repulsion is dominated, which you can kind of make a statistical argument about how the vortices will be arranged. I don't have time to go into the details of these asking after if you're interested. These things are completely analytic, and we suspect the real star to be somewhere in between. And when we do all the analysis, we see that the n-body scaling is bracketed by these two lines. So we're not entirely doing something in particular. And as the last one, I should say that are we going to see this? Well, the current thing that is about which is about yeah. So we're not going to see them anytime soon. But when we see them, well, if we see them, we can say a couple of things. First of all, we can say that glitches are probably caused by one punches. We can say that the neutron star interior is fluid, and if we can measure how strong the signal is, we can sort of figure out where which will tell us more about the physics of neutron star, which is very difficult to study on in terrestrial experiments. And finally, I'm just going to leave the reappear this. Um, yeah, that's about all of it. It was very quick. Thanks for the writing. I'm curious about dialogue. Yeah. Um, um, I I don't remember the frequency of Bella. It's 30 hertz, right? We can talk the numbers after. I don't. I'm pretty sure. Uh, I think Bella's pretty slow. Should be somewhere. Yeah. So, but depending on when it might be like for you to see in the next decade anyway. But yeah. Depending on the frequency band, really it would be better if it's better for me for if you get higher frequencies. But also when you get to really high frequencies like millisecond pulsars, they don't really glitch at all. So we're not really sure if the physics in the interior is different or not. But yeah, if you get much better detection, it also depends on the algorithm.